Hello everyone, this is Jenpeng. Today, we will start our journey of Lean Six Sigma, a series of courses developed by Mike Liang. We will systematically introduce the statistical principles and underlying logic involved in the Six Sigma. So, what is Six Sigma? First, Sigma is a Greek letter, and there are 24 Greek letters in total. Sigma is deepen, and most of the other letters will also be used throughout this series. Six Sigma denotes a level of quality. Assuming quality characteristics follow a normal distribution, which is a statistical term for a distribution that is symmetric around the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. And there are Six Sigma ranges between the process center and the upper and lower specification limits. Then, the red area represents the region where defects occur. We'll have a probability calculated as 2 in a billion. But in the long term, the processes will shift in location and distribution. A 1.5 shift represents a change in the data's central tendency. According to Motorola's experience, this roughly 1.5 sigma locational shift either to the left or right. During this shift, the range between the process center and the specification limits changes to encompass 7.5 sigma and 4.5 sigma. Then the defect probability becomes to what we're familiar with, 3.4 per million. Six Sigma also represents the Six Sigma methodology. It is a data-driven, systematic problem-solving methodology using the DMAI process, which stands for define, measure, analyze, improve, and control. It is a data-driven improvement cycle used for optimizing, improving, and stabilizing processes and designs. The Six Sigma methodology was developed by Motorola and popularized by General Motors, and it is now widely used and worldwide. The DMA process involves a significant amount of statistical knowledge, and it is challenging to understand and use. But trust me, I know exactly what you are suffering from because I have had the same experience before, so I know how to clearly explain the key statistical points and logic behind it. Before we get started, it is necessary to make some quick simple definitions. For example, a laser. Its power is one of its characteristics, and unit is milliwatts, where 800 is the value. Similarly, for salt water, one of its characteristics is volume, unit is milliliters, and 100 is the value. The population in statistics refers to the collection of all individuals we are interested in and want to study. In statistics, a population is the entire pool from which a statistical sample is drawn, and may include people, objects, events, etc. For example, all Model A lasers produced last week constitute a population. Since the number is limited and they are our only focus, this population is a finite population. If we wish to study all parts produced by machine A in the future, but we cannot obtain the parts made in the future, which makes this population infinite. In such cases of infinite populations, which means a population that is so large, it is effectively limitless, we must use the sampling method. But the sampling method is not only for infinite populations, even finite populations can be sampled as well. In statistics, parameters are key measures summarizing the characteristics of an entire population. Commonly used parameters are mean, standard deviation, and variance. Beyond these, there are other parameters such as proportion, kappa agreement, correlation coefficients, etc. The primary objective of statistical studies is to analyze and understand these population parameters. In the case of infinite populations, samples are drawn from the population, and then population parameters are estimated based on sample statistic. For example, using the sample mean to estimate the population mean, M, and the sample standard deviation to estimate the population standard deviation. The Six Sigma methodology drives decision-making through data analysis, and there are 4 different data types based on measurement scales including ratio, interval, ordinal, and nominal. The ordinal and nominal, also known as categorical data. Binary data is a special form of nominal data. Now, let's illustrate these data types with examples. Firstly, nominal data. For example, apples can be categorized into 3 types: red, green, and yellow. But these different types can't be compared for large or small. They can only be counted to calculate proportions. So as you can see, nominal data can provide information, but it provides very limited information. Another example of nominal data is team, such as team 1, team 2, and team 3. Binary data is a specific case of nominal data, which means it only has 2 outcomes. For example, either liking or not liking apples, or either good or bad apples. So binary data is a commonly encountered data type. Next we have ordinal data. For example, green apples can be categorized into 3 grades: 1, 2, and 3, with 1 being the best and 3 the worst. This introduces a sense of order, providing more information. For instance, we can record the number and frequency ratio. For example, we can determine grades 2 and above are acceptable, and the acceptable proportion is 95%. Ratio data is the most informative. For instance, if person A's height is 180 centimeters and person B's height is 216 centimeters, then we can say that B's height is 1.2 times of A. Since height has an absolute 0 point, the comparison of the ratios is meaningful, which is why it's called ratio data. So as you can see, this type of data provides very comprehensive information. And there are some other examples of ratio data. For example, weight and temperature in Kelvin. The last data type is interval data. In the previous example, if there is a third person, C, with a height of 140 centimeters, then the difference in height between A and C is 40 centimeters, and between B and C is 76 centimeters. While the differences are meaningful, but the ratios of these differences are not, because there are lack of an inherent 0 point. This is what defines as interval data. Celsius and Fahrenheit temperatures are other examples of interval data. Clearly, ratio data provides the most information and is of the highest level, followed by interval data. Nominal data provides the least amount of information. As we continue to explore other aspects of the Six Sigma methodology, understanding these parameters and their application will form the foundation of our ability to effectively utilize statistical tools. Thank you all for your attention, and I look forward to diving deeper into our learning journey together in the future.